Welcome to Exposure. The way weather has made headlines recently, it seems as if coping with extremes has become the norm for us. We are not as surprised by paralyzing floods and droughts as we were in the past. Is there a pattern behind these changes, or are they simply climatological blips? What's responsible for the swing from drought to deluge? El Nino.
The western edge of the United States, where land and water come together on the Pacific Rim. The beauty here is carved by the violence of irresistible water against immovable rock. The ocean gives this paradise its beauty, and the ocean sometimes takes it away. People are drawn to the water's edge like thirsty animals on a hot and dusty day. They seek a drink for the spirit, replenishment for the soul. The Pacific Ocean creates an ideal climate of sunshine and cool breezes and a lifestyle that depends on that climate. El Nino, a complex interaction of atmosphere and ocean. The phenomenon develops every 3 to 7 years and touches off drought and fire, floods and mudslides, short-term climate shifts that can cause havoc. It begins in the equatorial Pacific, 3,000 miles south of the United States. Until the 1980s, it came without warning, but has been a part of our climate since the beginning of human history. El Nino is born in the ocean off Peru, a powerful trigger for climate change that can affect 5 continents. El Nino was named by Peruvian fishermen centuries ago. They noticed that every few years, just before Christmas, their fishing grounds warmed. There were heavy rains, devastating floods in what is normally a coastal desert. And their staple catch, the anchovy, the one they counted on for survival, disappeared.
The whole fishery changes from one that is dominated by catches of anchovy and sardine to one that is dominated by catches of more exotic fish like the mahi-mahi and shrimp. Most of them will try to convert their gear to take advantage of what is available, but most of them just suffer terribly economically.
Francisco Chavez is a marine biologist from Peru. He lives and works now in Monterey, California.
This is the first real El Nino that I've seen off the coast of California, and I'm surprised at how similar it is to the phenomena that occurs off the coast of Peru. In terms of some of the more common species, for example, the salmon fishery has been very, very low. The sea lion's favorite food is squid, and squid has also been absent, and we're seeing a lot of the younger sea lions look like they're starving. They show signs of either being beat up by some of the older sea lions because they want to keep them away from whatever food there is. We've looked back into the historical record and seen evidence of it occurring way back into the time of the Incas. So it's been something that's been around for several hundred years, and it's probably been around for several thousands of years. So it's part of the normal cycle of our climate system.
The modern study of El Nino began in India at the turn of the century. The people of India depend heavily on their annual monsoons, seasonal rains created by pressure changes over the Indian Ocean. The 1899 monsoon season failed, and Sir Gilbert Walker, a British scientist, looked beyond India for the reason. He studied data from around the world and noticed that dramatic atmospheric pressure changes in Darwin, Australia, and in Tahiti seemed to coincide with changes in rainfall patterns in India. He named this phenomenon the Southern Oscillation, but he was not aware of the Peruvian El Nino, or the vital role of the ocean in this atmospheric seesaw. His work was dismissed by the scientific community and forgotten until the late 1950s. Then meteorologist Jacob Bjerknes began studying Pacific Ocean temperatures as part of an international team. By chance, he observed the 1957-58 El Nino. He concluded that ocean and atmosphere interact intimately, coupling to form one great climate engine, and that El Nino is just one element in a huge climate event, an event that includes the Southern Oscillation. In the scientific world, it became known as ENSO, the El Nino Southern Oscillation. To the public, it is El Nino. Its dimensions are enormous. At its largest, the El Nino warming covers a strip of ocean at the equator that is 1/4 of the circumference of the world. It affects weather from Florida to Peru to India. So to understand the El Nino, you'll need to understand how the world's weather works under normal conditions. Near the equator, oceans are warm. The water warms the air above it, and that makes the air rise. Rising air allows surface air to stream in from the north. The air then cools and sinks at about 30 degrees north, creates an area of high pressure, and sets up a full circle. This circulation is known as the Hadley cell. In the southern hemisphere, there's a mirror image of the northern hemisphere's circulation. There's a lot of moisture rising in the warm air near the equator. And of course, rising moist air cools and causes low pressure, instability, clouds, and rain. When you look at this pattern from a bird's eye view, you see two very important elements in our story. First, the clouds and rain formed by the merging rising air between the Hadley cells near the equator form a band of rain across the tropics known as the intertropical convergence zone. Second, because of the rotation of the Earth, the southward surface winds of the Hadley cells move around the high-pressure areas centered near 30 degrees and are deflected in a curve to the west. Those are the trade winds. The trade winds interact with the ocean's surface, pushing the warm surface waters from the east near South America to the west, toward Tahiti and Australia. That allows the cold water from the ocean's bottom to surface off the coast of Peru, and that's known as upwelling. Here's what it looks like in 3 dimensions. The warm water is very shallow off Peru, very deep off Australia. The trade winds are blowing toward the west, the ocean's surface. And the extensive clouds, rain, and storms form over that very warm western Pacific area. Those are the conditions across the tropical Pacific during non-El Nino years.
Part 2 of our story, When Exposures, continues.
Follow the directions on your TV screen. And El Nino gets its start in the South Pacific about a year before North America feels its effects. It's Christmas time in the first year of an El Nino. Along the coast of Peru, cold waters become a little warmer. The high-pressure centers in the central and southeastern Pacific weaken. And the air flowing away from the highs, the trade winds, weaken as well. Not a full El Nino yet. Not even a sure sign. It just means that something's up. But if the trade winds stay weak into March and April, there'll be less cold water upwelling off the coast of Peru. The sea surface temperatures there rise dramatically. And that unusual warming of the waters continues across the eastern Pacific. The red area you see here represents temperatures relative to normal. The rain and clouds that are normally heavy in the far western Pacific drift toward the central and eastern Pacific, drawn to the warming waters there. That means an extraordinary amount of rain in the eastern Pacific. Because of all the rising air, the convection in these stormy areas, the north-south Hadley circulation is strengthened. And that's how you get from the South American coast to the North American coast, caught up in the strength of the Hadley cell. By December of the second year, the warmth and the moisture from the El Nino merges with storms in the northern hemisphere, intensifies the subtropical jet stream, and pulls heavy rains all the way to the Gulf Coast of the U.S.
Here we have a sea surface temperature anomaly chart for the month of May.
Vern Kowski of the Climate Analysis Center keeps track of El Ninos for the National Weather Service.
There are 2 regions of the U.S. that are affected in a consistent manner. One is the area of the Gulf Coast states from West Texas on to into the southeast. That region normally is wetter than normal and slightly cooler than normal during an El Nino winter. That would be running from November through March. The other region which has a consistent signal is the area of the northern plains and the border states running from Washington through Minnesota and on up into western Canada. That entire region is warmer than normal during an El Nino winter.
That other region is affected by the northern branch of the jet stream. Normally, the jet stream leads storms and cold into the Pacific Northwest all winter. But the El Nino pushes that northern branch northward into the Yukon.
Man, we need air support real bad up here. They got anybody coming? Good. We need Marlboro evacuated and all the houses in the way. I don't think we're going to stop this thing.
Chief Manuel Navarro was in charge of the fire operations that day.
There's really no way to prepare for a fire of that magnitude. It really takes a life of its own.
Fire's totally out of control on several fronts. We've got at least 100 acres burning, trees, brush, houses.
The weather was a substantial factor.
Yeah, we're trapped between the lines of fire here. We got no water.
Within the first hour, 790 homes were burnt.
Haven, we have a woman on the phone. Her house is going up. She's an invalid.
Now, if you do just a little bit of math, in the city of Oakland, there are 23 fire engines. And so if you divide 790 by 23, it doesn't come out very well.
Don't put the Hill Area Disaster Plan into effect. We need get ready for mass evacuations. Affirmative. This fire is spreading in several directions. It's taken everything.
3,000 individual dwellings were destroyed that day in Oakland. 23 people died.
The city of Oakland and Berkeley and the Bay Area itself has a long history of wildland fires. 20 years ago, we had a fire in the Oakland Hills. We lost a number of homes, and it was located in the same spot where the fire started last year. So there's no question that people are aware of it. They may forget, but history seems to just keep repeating itself.
An El Nino often means heavy rains for some or most of the California coast. But the El Nino of 86-87 left California dry and marked the onset of a 6-year drought. And the El Nino of 91-92 dumped days of rain on Southern California, but too late and too far south to offer drought relief to Oakland. The Oakland fire was not the direct result of an El Nino. You see, an El Nino does not control weather events like individual rainstorms. It triggers climate change, the tendency or trend toward a certain kind of weather.
If we then look at something else like California, we find that the statistical relation is much weaker. Sometimes things happen one way, sometimes they happen another. What it means is that not that El Nino is not important for what happens there, but that it's definitely not the only game in town.
Just ahead, the conclusion of our story.
As of February 1st, the El Nino of 1991-92 had not touched the California coast. The relentless 6-year drought there seemed bound to continue. While Texas cities watched day after day of rains and floods, California was left high and dry. Then for 2 weeks in February, the Los Angeles area was deluged.
I see this type of thing where they show news pictures of floods in Texas and back in the Midwest and the East and so forth. It's just hard to imagine what does happen, and it happens very, very quickly.
Unbelievable how fast that water came up. And before we knew it, there was nowhere to go. All I could think of was hurry up with those choppers. I'm a lousy swimmer, and I don't know how long I can tread water out here.
We did 35 rescues of people that day, 4 dogs, 2 cats, and 2 birds. Our resources were stretched very thin.
It was the only major rain event in Southern California during the 1991-92 El Nino. Mudslides wiped out homes. Floods turned highways into raging rivers. 11 people were killed.
I've never seen it rain so hard in all my life in California.
And then the rain ended, and the climate in Southern California returned to what we think of as normal for the rest of the winter and spring. The El Nino continued in the South Pacific well into June. What you're seeing here are sea surface temperatures in the Pacific during the 91-92 El Nino, and predictions for those temperatures made 6, 9, and 12 months before the event. Stephen Zebiak is part of the team at Columbia University who designed this computer model. The model told Zebiak there would be an El Nino, but just what it would do to North America, and particularly the California coast, was more difficult to predict.
Perhaps the best way to think of it is it may mean that there's more of a tendency toward a particular pattern than there would be. It doesn't guarantee it, doesn't mean that the opposite can't happen. It just means that other factors aside, this makes a certain signal more likely to occur than it would otherwise.
No one predicted the El Nino of 1982-83, yet it was the most powerful of the century. Dust storms, fires, and drought in Australia, Africa, and Indonesia. Devastating rains and coastal storms in California, the Gulf Coast, and Peru. The global price tag, $40 billion.
There was a meeting of scientists, and at that time, an unofficial prediction was made by a leading scientist that there was no El Nino in sight. And in general, there was not a clue in this audience of people that was the most knowledgeable people in the world on this subject, that an event was even going to occur, let alone the largest of the century.
This three-dimensional model shows Pacific Ocean temperatures during that El Nino. At the time, there was no real-time data available from the South Pacific, so science was caught off guard. But after 1982, the National Oceanographic and Atmospheric Administration, NOAA, started the Tropical Ocean Global Atmosphere Project. So by the time the 1986 El Nino occurred, NOAA ships had scientific eyes throughout the tropical Pacific, instruments that measure the oceans and atmosphere and send home data via satellite every day. The 91-92 El Nino was predicted a year in advance. The success of the 91-92 predictions fanned the fires of enthusiasm throughout the scientific community. So El Nino is one of the most heavily studied climate phenomenons today.
You have, for the first time, the prospect of being able to receive a climate forecast that is useful to you in planning. That affects economics, that affects lives.
Perhaps the solution is to try to be ready to react to change, to be flexible, and to live life as though change is inevitable.
For places like the coast of Peru that are severely affected during these episodes, it's important that they adjust to that, because as a German writer said several years ago, there's two faces to El Nino. There are good sides to it and bad sides to it, and we have to be ready to take advantage of the good sides when they come along. So I think it's important for the population as a whole to understand that. There are opportunities during these events, and we've got to be ready to take advantage of them.
Weather is predictable. We can tell you with some measure of accuracy what your weather will do this afternoon, tomorrow, maybe the next day. We can show you pictures of weather on TV. But there is no videotape of climate changes like El Nino. Climate is a concept based on averages, statistics, including the broad swings of nature's pendulum, from desert dry to flooding rain. The California coast is just one example. Whole neighborhoods perch on mountainsides as though there will never be drought or deluge. But the wide extremes of the pendulum swing are part of climate as well.
El Nino is but one factor in the changes of weather across the globe. As we increase our understanding of the impact of El Nino and the other factors, we'll be much better at preparing for drought, deluge, and everything in between. Thank you for joining us on Exposures.